Looks like we need some backup on this one.
So, do you think you can help me?
Normally I'd use conventional methods, but that would hurt my LPE.
What would those be?
Normally I'd taste it or smell it, but I don't want to end up like that other poor fellow. But it's real simple. The process to which I can determine the identity of the compound.
Just get to the point. Do you know what it is or not?
Well, I could tell you the answer, but I think it would be much better to show you the process. There are 6 different processes to attain important details, also known as differentiating characteristics. There is thin layer chromatography, NMR, absorption spectroscopy, mass spectroscopy, gas chromatography, and FTIR. To start, we can eliminate absorption spectroscopy in our deduction process.
Why is that?
Well, absorption spectroscopy determines something called the lambda max, which corresponds to a specific wavelength in the visible color range. Since our initial mixture was colorless, absorption spectroscopy does not pertain.
Yeah, that makes sense. So, which process should we use next?
I went ahead and ran an FTIR card, which analyzes the different covalent bonds that exist within the mixture. Finding which covalent bonds exist allows us to eliminate a variety of molecules. In our case, FTIR shows that this mixture has CH, C double bond O, C single bond O, and C single bond C. However, there are no OH bonds.
Okay, so we can use FTIR to form a basic understanding of the bonds within a molecule structure.
Yep. After understanding what bonds exist within our mixture, we can look at the mass spectroscopy of the molecules composed. These mass spectroscopies will indicate the molecular mass of our molecule. The peak with the highest mass number, regardless of the height, is the molecular mass. In our case, we have 2 molecules, one with a molecular mass of 106 and the other of 101.
So you ran the NMR. What exactly did you find?
I found a few things. I found the different integrations and neighbors for each of the peaks along the NMR spectra. So for our first spectra, what I did is I separated them into 2 separate molecules because we have 2 molecules in our mixture. So for our first molecule, we have 3 peaks at 4.09 ppm, which indicates that we have 2 neighbors there. The next peak is at 1.64 ppm. It has approximately 5 peaks, which indicates 4 neighbors. The next peak is at 2.10 ppm, and it only has 2 peaks, which indicates 1 neighbor. And our last peak for the first molecule is at 0.97 ppm. And since there are 3 peaks, there are only 2 neighbors. For the second molecule, there are 2 separate ppm peaks, one at 1.41, and this one has 5 neighbors, and the next one at 5.14 ppm, and this one has no neighbors.
We're so close to the answer. If only there's a way to compare the strengths of the intermolecular forces between the 2 molecules.
Your deductive reasoning is incredible, Detective, because the next tool I used was gas chromatography. This method analyzes the retention time of the molecules and uses this to find the strength of intermolecular forces between itself and the mobile phase. A longer retention time would indicate higher intermolecular forces with itself. In our mixture, there is a retention time of 2.887 minutes. This lower retention time indicates lower intermolecular forces within the molecule and greater attraction to the mobile phase.
Why didn't I think of that? Of course. Although, there is one thing that's still bothering me though. What's the difference between GC and the other method that you're talking about, TLC?
In TLC, we also analyze the retention time in the mixture. However, this retention time is determined by the intermolecular forces between the tested mixture and the mobile phase, in which we combine the unknown substance. When I used this technique, I found that the mobile phase interacted more with the mixture than the mixture interacted with itself. We can therefore conclude that the mixture has lower intermolecular forces.
So, what am I missing?
You're not missing anything. You have all the differentiating characteristics you need to solve it.
Man, gotta do everything around here, huh? What am I even paying you for? First things first, absorbance spectroscopy. Absolutely useless, didn't give us any sort of valuable information. Thanks for that, by the way. Next, MS, mass spectroscopy, showed us that the molar masses of the molecules were 101 and 106 grams per mole. After that, we had FTIR. These showed us the bonds that were present in each of the molecules. These include CH, C, CO, and C double bond. After that, we had GS, S spectroscopy, and then that showed us the retention time of the molecules were 2.887 minutes. Additionally, TLC showed us that since the molecules moved with the mobile phase, it indicates the presence of low IMFs. Now, NMR, can you remind me of those values again?
Yeah, for the first molecule, our first value is 4.09 ppm with 2 neighbors, then 1.64 ppm with 4 neighbors, then 2.10 ppm with 1 neighbor, and then 0.97 ppm with 2 neighbors. The next molecule is 1.41 ppm with 5 neighbors, and 5.41 with 0 neighbors.
Now, let me see anything else.
Nope.
I've been playing your games for long enough. Now tell me, what is this mixture composed of? There are lives at stake here.
I mean, you have everything you need to determine this molecule. Please tell me.
Just tell me the answer, please.
Fine.
Thank you. Oh, of course. How could I have been so blind? The answer's so obvious now. So, the mixture is composed of N-propyl acetate and trimethyl orthoformate. Right, okay. Oh, but wait. I still need the mixture's percent composition by volume. How do we do that?
Oh, that's really quick. So the first step that you do to get the percent composition by volume is you take the area percentage with respect to the retention time. So in other words, you're going to take the area underneath the retention curve and divide it by the total volume. So in our case, we get 0.977 grams because that converts into mass. And after that, we find the densities of our 2 mixtures, or our 2 molecules. So our first one is N-propyl acetate, and that one has a density of 8,880 grams per milliliter. Trimethyl orthoformate has a density of 9,700 grams per milliliter. The third step is where we convert the mass into volume by using these densities. So we divide with 0.977 over our density. So for N-propyl acetate, we end up finding that the volume is 1.101 times 10 to the negative 4 milliliters. And for trimethyl orthoformate, we find that it's 1.008 times 10 to the negative 4 milliliters. In the fourth step, we take those 2 volumes that we found and we add them together to get a total volume, which in our case is 2.11 times 10 to the negative 4 milliliters. After that, we divide each of our volumes per molecule by the total volume and multiply them by 100 to get the percent volume, which in our case is, we get our percents to be 52.2% N-propyl acetate and 47.8% trimethyl orthoformate.
Alright, thanks. If I hurry up, you're still saving me.